Okay, well, there's our notorious danger sign in the book. When you see one of these, you know material's getting a little bit more tricky. It's certainly mathematically more tricky. And smoothing splines are a little bit more challenging mathematically, but they're beautiful as well. So let's talk about them. The takeaway message of a smoothing spline is a way of fitting splines without having to worry about knots. Okay? But it approaches a problem from a completely different point of view. What we have is we have this criterion that we fit to the data. So on the left here is the residual sum of squares. And so this part of it tries to make the function g, the argument of this criterion is a function, an unknown function g of x. And this tries to make g as close to what the observed y's as possible at each of the observed xi's. Okay? And we're searching over all functions. Now, if we didn't have the second term, we'd just pick any crazy interpolating function that visited every y exactly. So what the second term does is it constrains the functions over which we search to be smooth. And this is a somewhat complex penalty here, but what it is that the second derivative of the function squared integrated over the whole domain. Second derivatives are going to pick up wiggles of the function. It's going to pick up departures, for example, from linearity. And if you square it, it gets rid of the sign, and integrate means add them up. So it adds up all nonlinearities in the function. And this lambda is called the roughness penalty, and it modulates how much of this penalty you're imposing. Okay? And so we call it a tuning parameter, and lambda is bigger than or equal to 0. So the smaller lambda, the more wiggly the function can be. It means you're not putting that much weight on this penalty. And eventually, if lambda is 0, we'll get that interpolating function, because we won't pay any price for being wiggly, and so we may as well go through all the data. On the other hand, as lambda gets really large, if it gets off to infinity, so we want this, we pay a big price for any contribution from this term, the function will eventually be forced to be linear. Because a function that's linear has second derivative 0, and so this term would be 0 only. If lambda gets to infinity, we'd have to make this 0 to not be overwhelmed by this penalty, which means that the function's got to be linear. So this would be a linear model. So that's a really pretty way of setting up a smoothing problem, which gives us a whole range of values. As lambda goes from 0 to infinity, we get a range of solutions that are going to go from a linear function to a very wiggly function that goes through the data. We call the solution to that problem a smoothing spline, and it turns out, and the reason it's called a smoothing spline is that the solution is a spline, but it's a weird spline. It's got a knot at every single unique value of the x's, which sounds ridiculous when you first hear about it, but that's what it is. But it turns out that it's not as crazy a function as you like, because the roughness penalty controls how wiggly the function can be.
It's pretty amazing that this has a solution at all, right? It has a nice, simple solution.
Exactly.
And I guess a clue as to why it's a cubic spline is that the second derivative is in the function.
Yeah.
Right? And there's actually a whole family of splines, whereas if you have like a third, how does this work, Trevor? If it's a kth derivative, then it's this 2k plus first spline.
That's right. There's a whole hierarchy of families of these guys. Right. And it's crazy. I mean, if I hadn't heard of this and you showed me this problem and said, I want to solve this problem, I'd say, forget about it. Go and visit the math department. Yeah. Right? Well, actually, it was solved in the math department, but we're very glad they did that, because it's a very elegant.
And the proof isn't too hard, right, for those who are mathematically inclined. In our first, our big data mining book, the Statistical Learning, we have in an exercise, we have a sketch of that proof.
Right.
So if you like these kind of mathematical things, it's a fun proof to go through.
Yeah, and it might show up in one of the quizzes. No. Okay, a few details. As I said, smoothing splines avoid the knot selection issues, and we have a single lambda that needs to be chosen. That's quite attractive. rather than having to pick a whole bunch of different knots. The details are a little too complex to describe here, but fortunately we got a function in R called smooth.spline, and it'll fit a smoothing spline for you, and it takes some arguments, and and it's very easy to use. It turns out that when you fit a smoothing spline, if you take the fitted values at each of the observed x's and put those into a vector, which we call g hat of indexed by lambda here, you can write g hat lambda as a matrix times y, where y is the observed vector of responses. And S, of course, is going to be an n by n matrix. And S is determined by the positions of the x's and the particular value of lambda that you've used. Now, this is a special form. We call this a linear smoother because it's a linear operator times y. Linear regression, of course, is also a linear operator, so is polynomial regression, and all the methods we've talked about up till now, the cubic splines, all of them, result in expressions like this. But this one does as well. And that's somewhat important. It means that it's got mathematical properties that are attractive. And one of them is that we can compute something called the effective degrees of freedom. So, we've got knots at every observed data point here, and so potentially it sounds like, using our previous calculations, that there could be as many as n degrees of freedom. It's a natural cubic spline. But the degrees of freedom are much less because of the roughness penalty. And it turns out that the natural estimate for the degrees of freedom is the sum of the diagonal elements of this matrix. And that's the expression we've got over here. And we call those the effective degrees of freedom. So now when we use a smoothing spline, we can actually specify lambda by instead specifying the effective degrees of freedom. And a little bit of reverse engineering is done in the function to figure out what is the lambda that would result in such a degrees of freedom, right? And so it can figure it out. And so in R, it's as simple as that. You can say I want a smooth dot spline of age and wage. Wage is a response with degrees of freedom equals 10.
So the way to think of that, it's like a polynomial of degree 10, but it has about that complexity, but it's smoother. So the degrees of freedom are not all spent on 10 polynomial terms, rather spread out over the whole spectrum of the function, from smooth to rough.
Yeah. Very, very attractive way of fitting nonlinear functions. If you don't want to just fix the degrees of freedom, you can actually estimate the smoothing parameter by cross-validation. So leave one out, cross-validation is quite attractive for smoothing splines because there's a really nice expression, similar to what we got in linear regression, for the cross-validated sum of squares. So here's the expression. This is the sum of cross-validated residuals. This complicated looking thing here is the fitted smoothing spline if we leave out the ith data pair and evaluate it at the point xi, right? So that's a cross-validated fit. And to compute this whole expression over the sum of that, we'd have to leave out each point and refit the function each time. Well, it turns out you can just fit a smoothing spline to the original data and divide each of the residuals by 1 minus the corresponding diagonal element of that smoother matrix, right? So nice, it's like a magic formula. It computes a cross-validated, leave one out cross-validated residual sum of squares. And so you do this for a range of values of lambda and pick the value that minimizes it. So that's done automatically in the function smooth.spline if you don't specify lambda or the degrees of freedom. It'll just automatically use this cross-validation. So it's very attractive. Okay, so here's an example. These two functions look almost the same. One is using 16 degrees of freedom, fixed degrees of freedom for the smoothing spline. And the other ended up picking, it used leave one out cross-validation, and it ended up picking 6.8 degrees of freedom. So that probably raises some eyebrows. How can we have 0.8 degrees of freedom? 6.8. Well, the effective degrees of freedom formula doesn't guarantee you an integer, and so you can have effective degrees of freedom in non-integer values.